So let's talk a little bit about molecular orbitals in order to get ready to understand some of these pericyclic reactions. Just a reminder from general chemistry, molecular orbital theory is a little bit different than valence bond. What we do in molecular orbital theory is we take some atomic orbitals and we use mathematics that we don't go into the detail of. Quantum mechanics, I guess you can say, use it. And they take the orbitals and they mix them together using linear algebra. And when you do that, the number of atomic orbitals that go in will be always the amount of molecular orbitals that come out. And what we find is these molecular orbitals demonstrate that the location of the electrons that would fill them can oftentimes be found spread out and extended over multiple atoms in the molecule. And we saw that in the aromatic systems of benzene. Now, just like in benzene, when you do this, you get some combination of anti-bonding and bonding molecular orbitals. And as we saw in aromatics, there was even non-bonding orbitals. Now here in these conjugated dienes, we're going to mostly, we're only going to see either bonding or anti-bonding orbitals. Now here is an example. So I should say the first part right here, we have an example of just ethene. And so with ethene, what we have is two orbitals because we got two p orbitals going in that are doing the mixing. And we get one pi bonding orbital coming out and one anti-bonding molecular orbital coming out. And then according to Aufbau, we fill the lower energies first when we take the two electrons that were one in each of the p orbitals as the molecule was coming together and bonding, and we distribute those two electrons into the lower energy bonding molecular orbital. And we find the same thing happens here with butadiene. In this butadiene molecule, we have now 4 p orbitals going in, so we should see 4 molecular orbitals come out, and we do. And we find that they go from low energy to higher energy. And we also observe that as they go to higher energy, you see more and more nodes. You see no nodes in the lowest, 3 in the highest, and 1 then 2 as you go up in energy. So as you go up in energy, we do notice that the number of nodes is increasing. And we also see that the location of the node is symmetrically distributed. Now, I'm going to provide this to you as in the information part of the exams. And so it's always available to you. So mostly you want to try to be able to understand this material in how to use these charts. They show you where the electrons are distributed in both the ground state, as we're going to call it, and an excited state as we get into that. In butadiene, we find that the 4 p orbital electrons that are now the 4 pi electrons, we're going to do the same thing that we did in ethene and that we did in any of the diatomic atom molecules back in GChem and their molecular orbital diagram. And we're going to fill them from lowest energy to higher energy using the Aufbau principle. And what we find is we fill the first and second molecular orbitals with the 4 electrons. What that also demonstrates is it's an explanation of why the central sigma bond is shorter and stronger than you would typically expect for a single bond or for a sigma bond. And the reason for that is there's some electron density that is located between those two carbon atoms that you think, at least when you just look at the bond line formula, you think it's just a single sigma bond. There's some pi bond character, some double bond character that the molecular orbital theory shows exists between those two atoms. And so that electron density strengthens and shortens the distance between those two carbon atoms. So it doesn't have the typical carbon-carbon single sigma bond characteristics. Lastly, I just want to show you the 135 hexatriene molecular orbital. In that case, you've got these 6 carbon atoms that each have a p orbital in them. Same thing that happened in the last 2 examples. 6 p orbitals go in, 6 molecular orbitals come out, and it goes from lowest energy to highest. And we fill those molecular orbitals with the 6 pi electrons in the case of hexatriene, and the three lowest molecular orbitals will fill with those 6 electrons. And those 3 lowest molecular orbitals are also the bonding orbitals. Now, why do we delve into this here in organic chemistry? Well, the reason why we look at molecular orbital theory in organic chemistry is because it's a useful tool, kind of known as frontier orbital theory. It's a useful tool that helps us understand some reactions. And particularly, we're going to use this with the pericyclic reactions. We're going to find that in some cases, it's the ground state of these conjugated pi systems that are being used. And in other cases, it's the excited state if you're under a photochemical condition or if light is being exposed to it. And so just some useful terminology. We call the last orbital that you fill with electrons right here, we call it the highest occupied molecular orbital, or HOMO. And the lowest energy orbital that contains no electrons, we call it the lowest unoccupied molecular orbital, or LUMO. And so what we observe is when you excite the electrons in the ground state to the nearest excited state, you're taking the electrons from the ground state's highest occupied molecular orbital, and you're plopping it into what was originally the lowest unoccupied molecular orbital. And what that does is it actually redefines the system in that excited state so that orbital system, which now contains an electron where it didn't before, it's now the highest energy occupied molecular orbital. And so we're going to find that the HOMO and LUMO interaction is involved in some of these reactions. And so you need to know what conditions you're at and what the electronic configuration is in those cases. So let's take a look at this example. So the idea is just making sure you understand how to identify the HOMO and LUMO orbitals of butadiene. Now, in this case, we're saying under photochemical conditions. So in other words, light's being involved in this reaction. So here's the ground state molecular orbital diagram. So when you see that it's a photochemical, that is, that light is involved, and you'll notice that it's light when it's got H nu, it looks like an HV symbol, or maybe it just says light. And when that's the case, you always just say to yourself, okay, light's involved. One of the electrons, say for example in butadiene, in the psi2 has been excited to the psi3. So what that means, having been excited to the next level up, it's now the psi3 that's the HOMO, and the psi4 is now the LUMO. And the reason why it's important to identify not only where the electrons are and what the molecular orbital diagram is that's the highest occupied and the lowest unoccupied, it's not just like knowing it's psi3 or psi4, but we also want to know what the diagram looks like. And once again, it's not a memorized thing, you have the chart. But the reason we want to be able to identify this is because we're going to use these diagrams, and the idea, if you don't remember, the different coloring means whether or not, or I should say, which of those lobes are the same sign and opposite signs from each other. And that's going to be significant when we talk about these reactions where these orbitals are overlapping, such as in the pericyclic reactions. So now that we've talked about molecular orbital diagrams, now let's go over just an introduction of the pericyclic reactions. Now, pericyclic reactions is sort of its own category of what I kind of consider the 3 major categories of chemical reactions that we learn about in organic chemistry. We learn about what's known as ionic or polar reactions. That's the bulk of what we've seen so far. It's called ionic or polar because it involves locating and the interaction of these buildup of electron density and electron deficiency, or positive and negative charges in the various intermediates along the mechanism. Then there's the free radical mechanisms where it involves free radical intermediates and these reactions where you transfer single electrons or do some kind of bonding based on the transfer movement of single electrons. And then lastly, these pericyclic category. And so what defines pericyclic reactions? Well, let's first take a look at some of the categories, and then we'll try to lay out all the different aspects of it. So the first category is cycloaddition, also known, at least the one that we're going to specifically deal in, is known as the Diels-Alder. And what we see is already here, we have this cycle, or this cyclic rearrangement of electrons pi bonds, sigma bonds are forming, pi bonds are moving around, and that's what we're going to see is one of the aspects of a pericyclic reaction. So in this case, we got this molecule, this structure right here, and this structure right here coming together to form a new cyclic structure just by the rearrangement of their pi electrons. That's known as cycloaddition. Then you've got electrocyclic reactions. What happens here is it's sort of a ring closing. Sometimes it goes in reverse and it's a ring opening reaction. But once again, notice it's this cyclic rearrangement of electrons, mostly as you can see here in the pi electrons, either forming new pi bonds or forming new sigma bonds. Lastly, we have the sigmatropic rearrangement. In this case, we still have the cyclic movement of electrons around in a circle. And in this case, we've got some pi electrons and some sigma electrons, at least starting as sigma electrons, moving around. And then you have a formation of some new pi bonds and some new sigma bonds. So this is what a pericyclic reaction is ultimately characterized by. One, it's a concerted mechanism, meaning we don't go stepwise. We don't have step 1, step 2, step 3, etc., like we do in the polar or ionic reaction mechanisms. The mechanism, the single-step mechanism, involves a ring of electrons. That is this ring of electron flow. These pi electrons move here, these pi electrons move here, these pi electrons move here. Ultimately, they have to make it all the way around to be a pericyclic. In other words, the last movement of electrons has to fill in the empty spot that's generated by that first pair of electrons moving away from where it does. The transition state has to be cyclic. So this cyclic rearrangement leads to a cyclic transition state as the movement of the electrons occurs from reactants to product or products. And then lastly, the polarity of the solvent generally has no effect, whether it's aprotic, protic, polar, or nonpolar. It has no effect on the reaction rate. And the reason is because the transition state has very little buildup or deficiency in electron density, because it ultimately makes itself around so that as it's occurring, there's never really any buildup or loss of electron density in the transition state. And without that polarity in the transition state, the polarity of the solvent is going to have no effect on the chemical kinetics of that process. It's not going to affect the energy of the transition state. So one thing to end with to kind of help you define these three types of pericyclic reactions, what we notice is as these pi and sometimes sigma electrons are moving around and breaking some bonds and forming new, we see that there's a trend. When it's a cycloaddition, there is a gain in 2 sigma bonds and a loss of 2 pi bonds. For electrocyclic reactions, we have a gain of 1 sigma bond and a loss of 1 pi bond. And in the case of sigmatropic, we see neither a gain nor loss of either sigma or pi bonds. So by the end of that pericyclic movement of electrons, you reform the same number of sigma and pi bonds by the end of that process when it's sigmatropic, when it's a sigmatropic rearrangement. And so that is kind of the generalization of these 3 types of pericyclic reactions. So that's it for our introduction to pericyclic reactions. In our lecture, we'll be going over cycloaddition reactions, particularly the Diels-Alder. And then the following lecture, we'll delve into our electrocyclic and sigmatropic reactions. I hope this was helpful. I'll see you in class.